超酷的。Okay, so interesting stuff. Let's continue our lecture. So yes, last week we talked about several important things that we talk about how to determine the twist angle phi in different cross-section area and the different torsion, which is not pure torsion, okay, vary in torque, okay, and then very similar to what we taught in chapter 2, okay, we just cut the section that we are going to see how large, how great, or how small of the torsion it is, okay, we just cut it and we can determine the internal torque inside that, and then we can substitute all the equation to obtain the phi twist angle. And also last week we introduced the stress on inclined sections. It's really similar to what we learned in chapter 2, okay, and we have really similar proof procedure, okay, just stress times the corresponding area and then become force and then do the balance, and then we can get our result. And then after we obtain result, we found that we have sine and cosine, so we have maxima or minima, and then we can find that 45 degree will be the maximum for the pure torsion. So based on this pure torsion, we can connecting the E and G together. All right. So we use the cosine theorem. Okay, we can obtain the original shape with the diagonal line with square root 2h. After we do the distortion, we have LBD, and LBD has the relationship of the cosine theorem. And then we substitute all the epsilon mix equations formula, and then we can obtain that G equal to E over 2 times 1 plus nu. Okay, and then we also know that epsilon mix along 45 degree in pure torsion is half gamma. All right, and then this problem example tell us how to determine, how to draw the stress element, okay, stress element like this. And also the most important thing is that we taught you, guide you how to sketch the deformed element, the deformed element just like this. So previously you have original shape in a square, okay, in a square, and then after the deformation you may end up a shape like this, 平行四边形, or you can become a rectangle, okay? So all you need to do is just changing the value of it. I mean, change the shape, and then mark the epsilon and gamma mix, gamma, okay? Just mark all the value of it, and then you can draw the deformed elements. 总之就是你算出多少 epsilon max， 可能是 epsilon 1 或 epsilon 2， 但当然这边是 epsilon max 啦哈。那你就把它画出，你就照着它的长度 0.001 啊，把它画出来。那一个是缩短，一个是增长啊，大概就可以了。OK， yeah, how to identify this is compression or tensile. You can see this, yeah, here is compression, here is tensile. Okay, and then final things we mentioned in last week is the power concept of power. Okay, and then we just introduce some formula, and then we have a conclusion that higher speed requires a smaller diameter under the same power of the motor input. All right, then I'm going to finish this chapter today. Then you will see exactly the same path. Okay, path, really similar to chapter 2. Okay, you can see statically indeterminate torsion member. You can see this is really similar. 静不定, statically indeterminate structure. You can see that it fixed at a wall, and also an end plate will fix two material. The first one is bar 1, the other is tube 2. Okay, and then you have different cross section, and to find T1 and T2. Okay, so we need to find T1 and T2. We assume it go to the right hand side, positive. Okay, and then imagine that the T1 and T2, and also, oh, sorry, and then it should be T. So you have a combined system with torsion T, but we want to know what is T1 for bar only, and what is T2 for tube only. Okay, and then we want to see the phi 1 and phi 2. Okay, so let's take a look. So your bar 1 has T1, tube has T2, but combined together, you need to balance with T, right? So you can imagine that if you just write it down, that T1 plus T2 equal to the T, okay? Yeah, then the compatibility equation is that your end plate has fixed bar and tube together. So which means that phi 1 and phi 2 need to be the same. So phi 1 equal to phi 2. So this is the compatibility equation. Again, please don't remember this, okay? These compatibility equation and equilibrium equation are all based on the setup of the problem. You shouldn't remember all this, okay? Shouldn't do that. You need to see this and comes up by your imagination, or your, you need to think through it, okay? And then torque twist angle relationship, just like what we did in stress and strain relationship. So your phi 1 T1L divided by G1 IP1, phi 2 T2L G2 IP2. All right, so they need to be equal, right? So your T1 blah blah blah, T2 blah blah blah. All right, so again, you see that the result are very symmetry, 对称, right? Symmetry. You see the button are identical, but the top number of kind of symmetry, right? So again, this is just the logic flow, okay? You don't need to memorize it. I just want you to, don't you think this is really similar to chapter 2? Very similar, right? So I believe you know the concept. So now I am going to introduce example, and then you can directly understand what we are talking about. So now here, let me take a look. Reaction. Okay, so there is a problem looks like this, and then in the middle, the example has a T norm. Too big, sorry. T norm. All right. So this is the the problem. And you can imagine that this bar, this bar has two different cross section here and here. And in the middle, there it has a torsion T0. And then it asks us to determine the reactive torque TA and TB. TA and TB is due to the it's because of the fix of the wall, right? So now we can assume TA and TB has the value. Now, I receive a lot of students ask me, should we always assume to the positive direction for the force or for the torsion? I said, yes, you should do that, but you can do opposite. As long as you have your own system, it will be okay. So in this case, I will just give you a reversed assumption. I assume TA and TB to the left-hand side, to negative. No problem. We will still get the similar answer. All right. So similar. Don't worry about that. Okay. Now, again, for the statically indeterminate problem, that we need to have equilibrium equation. Okay, and you can see that TA and TB is negative 2. So I mean T0 minus TA minus TB equal to 0. So you can say TA plus TB equal to T0. Okay, this is easy. And the second is compatibility equation. Okay, equation. So you can imagine that these one bar with two sections, it fixed in between walls, two walls. So which means that the total phi should be 0, right? So the first section, phi 1, plus phi 2 need to be equal to 0 because it confined within with two walls. Okay, and then torsion angle of twist relationship. Okay, so wait a minute. Okay, so now we are going to see the internal torsion in section 1, internal torsion in section 2. So how can we do that? Because we are going to connecting phi 1. Phi 1 is here, right? Phi 2 is here. So we need to cut to determine the internal torsion. So the first one is we cut here, all right? We cut here and then we left the right-hand side. Okay. Okay. So if we leave right-hand side and then this one, you know, okay? And this is TB. And here we assume to the left-hand side, right? T1, okay? T1 is the section 1, internal torsion in section 1. So the T1 equal to T0 minus TB, right? And so we can substitute this to obtain phi 1. T0 minus TB and LA. You see, LA over GIPA. You see, here, the LA is this section, the section 1 length. We cut here, and we can determine the T1 in this section. Okay, in this section, every point in this section has the torsion T1. Okay, so T1 times LA, the length of LA, divided by G IPA. IPA is the cross-section of properties. Okay. Now let's take a look at the second section. The second section is that I use purple. So I cut the second cut, okay, and then we draw. Okay, we leave right hand side, and then this is TB, and this is T2, the section 2 internal torsion. Okay, and our T2 T2 equal to minus TB, and then we can have phi 2 equal to minus TB LB G IPB. Right, so then we can substitute this here. Okay, that's it. And we can continue. Okay, if we substitute this, we can have T0 minus TB equal to TB LB IPA. Well, ugly. LA IPB and TB equal to T0. Wow. LA IPB divided by LA IPB plus LB IPA. Okay, and then we can obtain TA equal to, hey, can I make it faster? TA T0 LB. This is LB. IPA. Yeah, that's it. So TA and TB reaction force, reaction torsion, just based on the just based on the torsion angle of twist relationship here. Okay, and then we use cutting method. We can see T1, T2 relationship, and then we substitute the phi here, and then substitute to the comparability equation. We can obtain TB and TA. So then we obtain the first problem: reactive torques TA and TB. Okay, TA and TB here, right? Okay, what is maxima shear stresses? Tau AC section 1 and tau CB section 2. What is the maxima shear stress? Well, maxima shear stress means surface, right? Surface. Okay, so which means that all we need to do is T times D over 2 and IP, but I'm not going to write all the stuff, but I believe you know the T here need to substitute T1 and T2 simultaneously. Okay, of course, tau AC is we substitute T1. Okay, and tau CB is for second section. So T2 substitute T, and half D, of course, this is half DA for section 1. For section 2, you need to substitute half DB, and your IP should be IPA and IPB for section 1 and 2 respectively. Okay, so you need to obtain your own value. For example, tau maxima tau maxima 1, so it should be 1 AC 1, T1 D1 IP1 or sorry, maybe A. Okay, sorry, this should be 1. All right， 听得懂吗？就是说这边啊，我就懒得写了哈。我只是说，如果你要，他的意思就是说要算第一段跟第二段的最大剪应力嘛。那最大剪应力其实是 surface 的剪应力。那 surface 的剪应力，那就是这边要带的是它的半径长，好是d2。那这边的 T 当然就是这边的 T1， 因为 T1 是第一节的内扭矩，然后 T2 是第二节的内扭矩，所以这边的 T 当然就是要带。如果你要算第一节的，你就要带 T1， 第二节就再带 T2。那第一节的话，这边当然就是 dA 除以2，那第二节的话，这边就是 dB 除以2 ，dA 跟 dB 嘛，哈。那这个 IP 当然就会是第一段的 IPA 或是第二段的 IPB， 就可以得到2个答案，一个是第一段的，一个是第二段的 tau max， 就这样 ，OK， 简单的。第三个 ，the third one, it requires to determine phi C. So phi C is actually one of it. You see phi 1 and phi 2, one of it. Although you know that these two has opposite sign. So phi C, you can just directly get TALA minus GIPA, or you can say TBLB GIPB. Okay, so basically, you can try that, examine that, they will be the same. Okay, they will be the same, the value will be the same. Okay, either you use the left hand side or right hand side, both are okay. Okay, you will get exactly the same value because phi 1, phi 2 somehow together become 0. All right, so that's how it works. Okay. Don't you think this is really similar to chapter 2? Very similar. All right. 我最近在 IG 啊或者 Facebook 上都会被推播一些很奇怪的东西。最近有没有发现有一个蛮流行的，就是那种很烂的3D 动画，然后很烂3D 动画就会教你一些奇怪的知识，就例如说，如果你遇到一个人，然后他就有一个3D 的很烂3D， 然后就拿着一个枪，然后说，如果你的手指去戳在那个枪里面，然后那个人开枪了，会怎么样呢？然后开始有那个很烂的动画。你有没有遇到这种？你有没有看到这种推播？没有，为什么你没有？为什么我会有？那你们推播到底是什么？我觉得这些，然后还有很奇怪的哦，就例如说，就是有一些很奇怪的事情，就是说啊，有一个人他在滑水道中间有一个支撑的杆子，就是那种柱子啦，哦，柱子是中空的，然后结果那个人就不走滑水道，他从那个柱子中间这样跳下去，就越陷越深，然后到最后爬不出来，所以到时候那个叫什么消防车啊什么，就是他就要去把那个整个滑水道拆开，去锯掉，然后才能把那个人救出来。 然后从头到尾这个东西都是用3D 的很烂的动画做出来的，然后就就来教我一些事情，说啊不要去玩这些事情。你们都没有发现这种东西吗？可能是年龄层不同，推波不一样。然后我觉得哇，这谁去做这些烂影片啊？到底为什么会有这种烂影片？然后但是好像又教了你一些什么事情，就觉得还蛮好玩的啊。所以你们都推播什么啊？你们都你们不会有一些推播到就是很好笑的事情吗？就是为什么要推播给我这个东西？而且还有一次，我可以跟大家分享一个，就是手机它真的会偷听人哦，偷听人讲话哦，你有感觉吗？你们都没感觉吗？手机会偷听讲话，就是说啊，我我跟朋友在聊天，就聊到医美，就聊到眼袋，然后就是要可能做眼袋这样，结果过了第二天，我就被推播医美眼袋，然后就有一个男生的那个就是老明星，然后就这样，嘿，很好看这样。然后我想说，这就是一个完全的证据，因为我从来没有搜寻过医美，这好，我从来没有搜寻过医美，但是他就推播给我这个东西。那而且我从来没有想过眼袋是什么，甚至我连眼袋是什么东西我都不知道。那但是因为跟朋友聊完天以后，然后他就推播我眼袋，很厉害的，真的。那对，我觉得蛮酷的。但是很有趣的事情是，那一桌有很多人，那一桌有很多人，那其他的人就没有被推播，所以他还是有分的。也就是说，他认为我可能会对医美有兴趣，但是可能另外一个人他就不会对医美有兴趣，还蛮有趣的，就是呃是也蛮准的啦，就是我相对来说也是比较爱漂亮嘛，就是比较就是会注重一下啊，注重一下这样，但是就是电脑它竟然都知道这件事情，但是我真的没有搜寻过叫什么眼袋啦，对我没有搜寻过眼袋医美什么都没有搜寻，但他认为我是有兴趣的，嗯，真的太有趣了。Just tell you that your cell phone will listen to you always. Okay, next. Then you see that this is strength energy in torsion in pure shear. Okay, strength energy. Don't you think this is really similar to chapter 2? Strength energy done by torsion. Very similar. Okay, very similar. Again, a bar with torsion T, okay, with the rotation angle phi, twist angle phi. So phi equal to TL divided by GIP. No problem at all. You know that, right? So again, your strength energy will be your torque in y-axis, and x is your angle of twist. And then your U, the internal energy, strength energy, U will be equal to the work you done into the system. So you have T times phi divided by 2. So the area will be the work you done. Okay? And work you done will ideally equal to the stored energy in the material, which called strength energy. Okay, very similar. You can imagine that in chapter 2, here is force, here is displacement. Okay, so your strength energy, U equal to W times equal to T times phi divided by 2. Okay, and you can substitute this phi, your phi to here, phi, and then you can get this one, or you can substitute the T here to here. You can get up different form of that, but you get the idea, right? Strain energy just equal to the area of the torsion and angle of twist diagram. Okay, very similar to what we learned before. And then your strain energy in non-uniform torsion is also similar to previously. You have different section, so you just sum them up together, and then you can get the total strain energy. And you have the gradual change cross section. You just need to find the IP as a function of x, and your torsion has been changing. So you need to find the torsion as a function of x, vary with x, and then you can do the integration. You can get the total u. Very similar what we learned before in chapter 2. So I guess we can skip this quite quickly. Next one, again, we are going to obtain the strain energy density. Okay, strain energy density. So strain energy density here, you can see this is the standard stress element with the pure shear. Okay, and you see this is a positive. All right, and please allow me to make it 3D. All right, 3D. Okay. So now, I will make it T, the thickness, okay, with the height. Now, after the shear, the square will be deformed into this shape, 平行四边形. All right. So I guess I really need to know how to say the vocabulary of 平行四边形，因为我们一直在持续用到它，我应该要多学学的。Yeah, do you know？我查一下，不能一直在讲 this shape，实在太逊了。平行四边形。
Parallelogram.
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 Parallelogram. Parallelogram. Parallelogram. 平行四边形。太难了吧 ？Parallelogram. 平行四边形。All right. So the square become parallelogram. Okay. After shear stress. Shear stress. Parallelogram. Okay. And the original angle will be half pi and then become half pi minus gamma. Okay. And then again, you see 95% of the procedure in mechanics or materials is stress times area. Okay. And then become force. So here, shear force. This V here is shear force. Shear force equal to tau h t. What is t? ht here is this, right? ht is this. So tau ht. So you see tau times the shear stress times the area is shear force, V. Okay, so all the face are the same. So you have V, 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 V. So it becomes shear force. You see these two figures are really similar, but the other is tau. The left-hand side is tau, the right-hand side is V. They are shear stress and shear force. The only difference is that this times area. Okay? Then if we put this parallelogram into the floor, okay? So kind of put it down into the floor, and then you can notice that there has a triangle here, and this height will be delta. Okay, so you can imagine that this pizza shape the arc can be the delta equal to gamma times the h. So the delta here approximately equal to gamma h. Right. So now we know that the work, you see the work is going to the right-hand side, the V push from left to the right, and the force will mix this displacement delta. So the work is V times delta divided by 2. So you see that you can imagine that actually this doesn't induce any direction, any displacement. This, no displacement, only this one. So remember that single load, single displacement in a single direction. So you can make only one contribution here. One contribution go to the work. OK， 还记得我们之前说的一个力量只有一个方向的位移。你看，就只有这样，这边有位移，其他都没有啊。你看这边其他这边都没有，这三个都没有。虽然有力，但它没有位移，所以不做功。所以这边所做的功会全部变成这个 strain energy 里面储存的材料储存的 strain energy。OK， so only one contribution, V times delta divided by 2. So U equal to V delta divided by 2, and then you can substitute all this into here, and you can get this ugly form. Okay, then this is strain energy. And strain energy density, what is that? The strain energy density, the definition of that is strain energy divided by unit volume. Okay, unit volume, and become small letter of U. So capital U divided by V naught. Okay, V naught is not shear force. Okay, although they have V, but the first one is shear force. The other is volume. Okay, so notice that the V naught here is volume. All right, the volume is the original volume is H T. H times T. This volume, right? So your U here, substitute here, and then divide by HT. And then you can get tau gamma divided by 2. You see, very similar to chapter 2. All right? Oh, okay. So you see shear force, displacement divided by 2. Here is tau is shear stress, and shear strain divided by 2. Very similar to chapter 2 we learned. Okay. And again, your gamma can be referred to tau divided by G, or your tau can be referred to G times gamma. So you can have two different forms of strength energy density. Very similar to what we learned in chapter 2. All right, so I guess all you, I mean, you understand this. No problem at all. Okay, easy, right? Okay, 4 minutes. Let's get into the next example. Next example is easy, and you will see that, wow, very similar to chapter 2. I have repeated this phrase for several times. You have 3 cases. The first one is TA. The other is changing to TB. And the third is TB and TA together. Then I believe you know what the purpose of the example is. It gonna tell you that the energy cannot be superposition, cannot be added directly. Okay, remember I have exactly the same type of example in chapter 2. So the first one, they have some properties, TA, TB, LG, IP, blah, 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 and find the strength energy. Okay, so the first one, UA strength energy, easy because it just follow the value 2GIP equal to 100 squared times 1.6 and 2 times 80 times 10 to 9 times 79.52 times 10 to 9. Okay, and then the value will be 1.26 joule. The second one, UB TB2 divided by 2GIP. Okay, here it's a little bit need to be note. Okay, what do you think? This TB squared times the length. The length should be what? Anyone for the bonus? It should be what? Although this is L, but which one? Divided by 2. Very nice. Very nice. Yes. L divided by 2. What is your number? Yes. 13019. Good. Very good. Yes, exactly. You can see that there's no force at all in this region. So no internal torque inside that region. So your U only store in the first part. All right. So after that, we have 1.41 joule. Okay. And then I am going to continue after 10 minutes for UC. Okay. And yeah, I will see you later. If you have any questions, just come here. 继续上课。Okay. Okay, so let's continue. So we just finished this UA and UB. UA is as torsion TA, and the second part is TB, acting on the at the center. Okay, and UC is combined together. Combine these two cases. So let's take a look. So we need to know that because there are two section of that, so we need to cut. Okay, and we leave the right hand side. Of course, you leave the left hand side is okay. And because second part, and we have okay. Then TA, and this is T1, okay, and this is TA, and this is TB, and this is T2. Okay, so you notice that I'm using T1 and T2 to the left hand side, and you can do right hand side, of course, right hand side. Assume to right hand side, no worry. Okay, as long as you follow your systematic procedure, if you determine in the end TA become T1 negative, I mean, no problem. All is okay, right? Next. Then you can see that the TA, sorry, the TA is the first section. TA square L over 2, because you only determine the first, I mean the right hand side, right section, TA. And T1 and TA are equal, right? So 2 GIP and plus TA plus TB. And you know that where it's come from, TA plus TB. So T2 must be TA plus TB. Okay? And square L over 2 in the first section, and 2 GIP. And then after that, you have T. Can I make it? Can I do the shortcut again? All right. Okay. Yeah. Yeah. And then plus TATBL divided by 2 GIP. All right. Again, you notice that the value will be 1.26 plus 1.89 plus 1.41. Okay? So now let's take a look. Yellow, 1.41, 1.41. And blue, 1.26, 1.26. And 1.09 is actually additional term. So again, although these two loads are combined, TA plus TB equal to the case like this, but your energy cannot sum them out together. You need to have a one more extra term. You cannot add in the strength energy part. You cannot do that. You cannot directly sum them up together. All right. So that's the concept that we learned in the previous chapter, and we just want you to know that they are really they can be used here as well. They apply to here as well. All right. So almost there. Chapter 3 is almost there, and chapter 4 will be fun. Okay, I will say chapter 4 is quite fun because chapter 4 is just doing drawing. Okay, drawing the figures. It is called moment shear moment diagram. We just plot. We just draw it. Okay, so it's quite fun, and the value, sorry, the calculation is not that hard, not very difficult. Okay, but the concept is important. So let's take a look. I believe you quite understand this, right? Because we've done that in chapter 2. So, and yeah, again, after we've done the chapter 2, chapter 3, we need to have midterm 1 next week. Oh, by the way, tomorrow morning we will handing back your quiz 1 sheet, and then Li Jun will come here and give you return your exam sheet. And if you have any question or problem, Li Jun will come back again around after the course, okay? And then you need to discuss with her, and if you have problem with that, the mark. All right, next, final example in chapter 3, very similar to what we learned before, right? But this time it become a torsion. T here, and again, you know that this is dA, this is dB, and phi A, okay, phi A, and so this is some sort of cone, but without the tip, okay? So we need to find the phi A, okay? Phi A is here. Again, because the cross section is changing, so their IP will be changed as well. So we need to find the IPX. We need to find IP of X. The IP will change following X. So what is IPX? We need to find diameter of function of X, because IPs, you know that pi d to power 4 divided by 32, right? So if you want to find the IP of X, you need to find dx as first, and we can use the method in chapter 2, right? We know we have done this before. PDF page 10, right? We've done this before. Last time we make it become cone, right? And then we have the origin here, and then this is LA and this is LB. Remember that, right? But this time I'm going to use different method. Okay, different method. Well, similar. All right. So what I'm doing here is I'm going to cut this shape by two triangle. and combine them together. Okay? I want to make this one combine together, all right? And you will see this one is dB minus dA because the middle cone is gone, right? And here, this is dx minus dA, right? And of course, this is x, all right? And this is L. Okay, so all I need, what I have done here is only taking out this cone in the middle, take away, and we assemble the upper triangle and lower triangle together. And so all the dx become minus dA, dB become dB minus dA. Okay, and if you can understand this, we can use similar triangle again. Dx minus dA divided by x. The ratio will be equal to each other, right? For the similar triangle, dB minus dA L. So your dx equal to dA plus dB minus dE minus dA divided by L times x. Okay, so that's it. And the good thing is that, well, later, okay. So after I have done determine the dx, we can obtain IPX, right? IPX pi over 32, right? And dx 4. And pi 32. Wow, a little bit big. dA plus dB minus dA divided by L x 4. Okay, so this is IPX. Okay, so we are going to integrating them and to obtain the internal strain energy. The good thing is that in this setup, there's an advantage of this, because remember last time our lower limit is not really, it's a little bit tricky, right? But now today, this is okay. The reason why is that our x does start at the beginning of the x equal to 0. Okay, previously in our method in chapter 2, we extend our x origin to the left hand side. So our integration lower limit need to be start from LA, right? Last time. But now, because we didn't extend our origin, we can start from 0. So you need to know that the form of dx here is different from the chapter 2. Okay, 听得懂吗？就做这件事情是有好处的。我们第二章不是有做一个这样子的形式吗？那时候我们把我们的原点跑到左边去了，所以我们在积分的时候，我们那时候是从 LA 开始积的，那要小心。但是这一次不一样，这次我们没有去做任何的延伸，我们直接就是把它并在这边从零开始，所以呢，我们就可以从零积到 L， 哦，那比较干净，比较方便，比较叫什么？比较叫什么？比较优雅了哦，比较优雅。OK，好，好，那接下来right. Next one, let's continue. So tx square dx, okay? And 2gipx. Let me make it smaller. And equal to 16t squared divided by, luckily tx is constant, okay? Pi g. And L0 dx dA plus dB minus dA divided by Lx4. Okay? Then 16t squared L. Wow. 3 pi g dB minus dA d dA is 3 minus d. Wow, terrible. D, B, 3. Okay, so that's it. All right. Oh, by the way, after we've done the U here, our goal is phi A. Our goal is phi A. What's the relationship between phi A and U? A, okay. Now, U equal to W equal to half T phi. Okay, so our phi A equal to 32 TL divided by 3 pi g dB minus dA, okay, and 1 dA3 minus dB3. Wow, difficult. Okay, so that's the result. We can determine phi A. Well, okay, so that's the result. Okay. And then we finish the chapter 3. Congratulations. 春假的时候，我去小琉球。去小琉球干嘛？我去潜水。有没有人去潜过水？潜过水吗？真的啊，水费的，要考照的。哦，我去考了一个照，我在过年的时候去考照。然后我是一个非常容易紧张的人，我都会觉得说，我没事人好好的，干嘛每次要把自己放在有可能淹死的地方？这样，但，真的很棒啊，真的很棒，在水里面，哎，在小琉球可以看到海龟哦， 然后还蛮疗愈，就真的蛮可爱的，就在那边游来游去。我有看到河豚，我有看到海星啊，还有鳗鱼啊，是鳗鱼吗？反正就是很多蛮酷的生物这样。然后你知道最厉害的小琉球的潜水最厉害的地方，最让我感到厉害的地方是什么吗？就是在中间休息的时候，他会给你贡丸汤。哇，他就一大桶贡丸汤，然后大家就是边喝，然后就是开始吃，你会觉得哇，这真的是人间美味。因为你就游泳嘛，就很累啊，然后你真的起来的时候吃个热汤，真的很棒。好，那就台湾的旅游，虽然的确是蛮贵的，哦，的确是真的是蛮贵的，但是有一些细节，就让我还是觉得蛮贴心的。就例如说刚刚的贡丸汤，被一碗小小的贡丸汤就会收买了这样，但实际上是真蛮贵的。那就还蛮好玩的嘿。然后在水里面，然后还去看沉船。那沉船它就是会有一条线跟你的那条就是就那条线会跟你的船真正的没有沉的船，没有沉的船跟沉的船有一条线，然后就拿那条线抓到线上线，这样慢慢的下潜，这样好好玩哦。然后就有那种铁达尼号的感觉，哎，蛮酷的。呃，还有什么？呃，然后当然会有导游嘛，因为我哪敢自己人下去啊，哈，所以有导游，导游会帮我拍照啊，这样。然后，然后我就会看到自己在那边就很挫，因为你在海里面就很紧张嘛，我就很紧张，然后我就动作都很蠢这样，然后表情也很糟这样，然后呃然后就要学着呼吸，然后我就太紧张了，我的呼吸的那个氧气瓶耗氧量都比别人还要快，这样，所以我都会拖累大家哦。大家明明就剩很多，但是因为我剩很少，所以我们就得走了。我们要以那个团队要以耗氧量最少为准嘛。你总不能说，哎，我还没有到达要回去的地步，但是他已经到达了。那我才不理他嘞，那这样他就会死嘞。所以说我们大家都要依照他的状况，所以我每次都是那个害大家要提早走的人。就是我，因为我的吸气就是一直，然后对，我要重新学习如何吸气这样。那潜水真的是一个蛮好玩的事情，好玩，然后但是真的很恐怖。当我在考照的时候，有一度在水里面呛到，然后水整个灌到我嘴巴里面去，然后那时候我就觉得，我好想念陆地哦，我好想回去哦。但你又不能直接冲上去啊，你冲上去的话，你会那个潜水夫病，所以就只好忍着这个压力，然后要在水底下这样，啊，真的蛮恐怖的。不过呃，多学一项技能啊，我是觉得蛮好玩的。大家有未来有钱有闲的时候，可以试试看这个，我是觉得真是一个好的体验哦。Diving is good，好，结束。Okay, next, finish chapter 3. Let's go for chapter 4. Fun chapter. Okay, this is a fun chapter. We are going to draw a figure for shear force diagram and bending moment diagram. Okay, 剪力弯曲. So now we are going to see a beam element bear the lateral loads. What is lateral? This is axial. Axial 轴向. What is lateral? Lateral. Okay, so the lateral loads are all in the XY surface. Okay, XY plane. Okay, so you can see that here. Sorry. Here. Okay, or here. Here. Okay, or here. uniform load. Okay, so they are all lateral loads. Okay, so the loading will make this beam. I will say beam. What is beam? 梁啦. That. Okay, this. Okay, they are all beams. So you can imagine that people on the third floor, okay, third floor, they are standing on that beam. So the beam will just so the people just like this, okay, and maybe this is a desk, okay, sitting on the beam. So the beam should be looks like this. Although you cannot see anything, if you think your building, your beam looks like this, let's go. Let's escape from this building. But although this deformation is exaggerate, okay, 夸大了, okay. Now we are going, and also another thing is that this is this one also another case, okay, and maybe we have the force here, and it will bend like this, bending, okay, the bending. And you notice that there has different symbol for this. I will introduce all this, okay, to you later. So in this chapter, we're going to guide you to draw shear force diagram and bending moment diagram. This is the most important things. And maybe you're thinking why we're going to understand this kind of civil engineering, architecture loading. Why? We have material science engineering. Why we need to see this? Why we need to learn this? Actually, we have many this shear moment diagram also can apply to the mini size, also apply to mini size. What does that mean? For example, have you heard about AFM? AFM's atomic force microscopic, right? What is the mechanics of this? Actually, it is a beam, small beam, and with a tip at the, a needle at the tip. And this material is piezoelectric material. Okay, what is piezoelectric material? Piezoelectric material, 压电材料, which can convert deformation into voltage. Okay, so if this tip touch the material surface, okay, and it will push this piezoelectric material, push, so it will generating shear or bending, and then it will generating voltage. So the voltage signal can be collect, and then we can know that how the deformation. And then if you know the deformation, you can convert this information to construct the surface of the material. 这样听得懂吗？就是压电材料会把位移转换成电，电是可以量测的嘛，所以你必须要知道这些电跟它的位移的关系。应该说电跟位移之间的关系我们已经知道了，但是这个位移必须要怎么样去反映出这个地板的这个材料表面的起伏，那就必须要去看我们的 bending 啊、shear 啊、force 这样的 ，OK？ 所以不管怎么样，这边学到的力不是只有在 大的东西才可以看到，小的东西也可以看到。材料力学为什么是材料力学？因为它跟材料是非常有相关性的啊，所以也是跟微小的东西是可以应用在上面。All right, so let's continue. So, we are going to introduce the beam, loads, and reaction types. Okay. Type of support. Support is something make this beam here. If there's no support, it will fly away. Okay, so there must be some support to generating the reaction force. Okay. Now, firstly, I'm going to introduce the axis. Okay, axis X and Y. When you see this, you can see that this is just like a, side view. Okay, so X and Y. This is X and this is Y. And all the load is on the XY plane. Okay, so again, you can see the load are all on the XY plane. Okay, on the XY plane. Right, so I'm going to introduce, if there's no the support here, and if you apply the load like this, it will fly away, right? So these supports will give you a reaction force and make it balance, and then it will stay here to let you see it. Okay, so now here I will introduce, this is point A, this is point B. Sorry, I will make it to the left a bit. Okay, so now I will firstly introduce pin support. Pin support, I will give you a symbol, triangle symbol. Triangle symbol. It's a pin support. Pin, 大头钉. Okay, just like pin on the wall. Okay, with the two fingers. Ding. All right. So we also call this hinge. Hinge support. In Chinese, 消之城. Okay. You can imagine that the point A with the pin support, we have a pin, 大头钉, pin on the wall, just like your two finger, fix a bar, fix a beam, and you cannot make it left and right, cannot up and down. No. So X and Y are constrained. So what does that mean? Which means that it will provide RV, vertical reaction, and provide horizontal. Okay, so RH, I will say A, RV, A. So pin support, 消之城, will give you two reaction forces. Okay, X, Y direction. Okay, next one. It's called roller support. Roller support can be either, looks like this. You can see there are three circles. So you can see this is roller, or you can just draw one circle. Okay, you can see that this is roller. You can just like a train track. Okay, it will, just like a train track, you can move along X direction, but you cannot off the track. So you only give a vertical reaction force, but no horizontal reaction force, because you can do the left and right movement. Okay, this is a roller support. Roller support has provide one reaction force for Y direction. You can imagine that roller support just like a track, train track. The train track can do left and right, but it cannot off the track. You cannot jump off the track. Okay? So it's roller support. Then here, this beam, we call that simply supported beam, 减支梁, because this is the kind of the most simplest one that the beam can stay there for stable, okay, stability. Okay, because it can make it, support on the ground and also fix one end. Okay, that's good. So this is simply support beam. Here is called cantilever beam, 悬臂梁, just like your arm doing this, and our body is the wall. Okay, this is a wall. The wall is fixed support. Okay, fixed support here. You can imagine that, of course, the force maybe looks like this, or maybe looks like that. No problem. Just random draw. Okay, it doesn't matter. Okay, and the fixed support, just imagine that your hand directly grab the bar. Okay, so it cannot be left and right, no. Up and down, no. And rotate, no. But in a pin, yes, you can rotate. Okay, so fix, you cannot do anything. All right, so it will give you fixed support RV and RH. And the most importantly, it will give a reaction moment. Reaction moment. This is really important. Okay, reaction moment. So I will say this fixed support give you 3 reaction forces. Okay, X, Y, and M. Okay. Sorry, I should give you a symbol. It's A, RV, A, RH, A. All right, so 3 types of support, very important. Okay, and overhanging beam, 外升梁. Wow, you can see that here. This is not entirely cantilever, and this is not really a simply support beam. Well, just you have a overhanging beam here. And so now take a look. This is P, all right? And if there's a moment like this and 1, okay? So now I can tell you directly here, there was give 2 reaction force, and this is roller, so only have 1 force. And again, you see there's no horizontal force. So actually, in this case, here become 0. Okay, so your reaction force are not necessarily be there. Your reaction force based on the loading. If the loading is not in horizontal, you don't need to have any reaction force in horizontal direction. Okay, that's it. So in this page, we introduce the type of beam, 剪支梁, simply support beam, cantilever beam, 悬臂梁, and overhanging beam, but this is not actually important. The most important thing in this page is pin support, roller support, fixed support. Okay, these three things, pin give you two direction reaction force, X and Y, and roller support give you Y direction reaction force, and fixed support give you three of them, X, Y, and moment. Okay. Now, I believe you understand this, right? This is not difficult. Then I'm going to introduce loads. And all these loads, actually, you learned that before. So don't worry about this. Okay. Right. Next. Types of loads. Point loads, P1, P2, P3, P4. Well, actually, we learned this in chapter 1, maybe, unit N. Okay. What's that? P1, P2. All right, so you can see P1, P2, and P3. It's not important. I mean, I just give you some example. Just P1, P2, P3, P4. All right. They are all point loads, normal condition. And you know the distributed load Q, right? Which with unit nu divided by m. So U divided by Newton divided by m is actually, the Q is not a load. It's a you need to times length, and it will become the load. So this is Q, and only when you times the length, and you will have QC. The QC is load, okay? And this is effective load, okay? It is very important. I will let you know that when we do the force balance, we simplify distributed load into an effective point load. Through the centroid of the area. This is really important. Okay, so when we do the force balance, we simplify the distribution load into an effective point load through the centroid of the area. Okay, you see here, this is a distributed load. And then we simplified it into the QC, is a effective load, and the position will locate at the centroid of this area here. Okay, so the point load here is actually half C. All right, this is really important. So when you do the force balance, okay, and here and here, okay. When you do the force balance in this, for example, P2 and P1 sine theta maybe, and QC here, and you need to balance with these two force, right? So these 5 forces need to be balanced, okay? So, and also moment need to be balanced, right? So these QC represent here and then through the centroid. 这边超重要的哈，我们在做力学平衡的时候，我们不会去做分布载重，我们会把分布载重简化成一个等效的力，而那个等效力作用的位置，等效的点力哦 ，point load 哦，点力哦，而它那个力的作用的位置在哪里？在这个形状的行星，它会通过这个形状的行星 ，OK。这是积分后的结果了哈。那它所以，例如说像这个地方它是长 C 嘛哈，所以这个 QC 它作用的位置就是在从右边数来的 C/2 的位置。那这个有什么用？有，你会关系到你的弯举的力平衡哦，弯举平衡，因为它会有它的力倍嘛，所以这边是非常重要哦。那千万不要用这个东西来去做积分，也不要去弄了一个等效应力以后，然后再把那个分布应力就踩上去，不对，因为这个分布载重的全部都已经被你简化成一个 QC 了，好，所以千万不能2个都算哦，那很奇怪，你就会 double 算，而且你也很难算。总之就是在做 balance 的时候必须要这样做。OK，be careful. Okay, let's continue about the concept of the centroid of the area. So imagine that if you have a gradually increased distributed load, what can we do? You know that because we can simplify this, so we can have 2 area. So this, if you have Q1 and this is Q2, okay? So the Q1 gradually become Q2, all right? And then the first area here, sorry, will penetrate the centroid of green origin part, Q1B. This is B. And the green part will be penetrate the centroid of triangle. So it should be Q1, Q2 minus Q1 divided by B divided by 2. And the B over 3, right? Because centroid of the triangle will be B over 3. Okay, so that's all for today. I will see you tomorrow. Okay, if you have any questions, just come here. Thank you.
创意材料的课程，
哎，怎么说？
那个创意材料的课程
是
7月初第二个然后什么的。
OK，
我想问你，就是7月1号到7月5号有意愿来上课？
应该是没有问题吧？等我一下哦。Record, stop recording.